Welcome back. So as I told you in the previous vignette, what we're in the process of doing is just really trying to review the nature of the drive towards equilibrium of systems left to themselves, and we're kind of holding it up and viewing it from a bunch of different perspectives. I think, as I tried to highlight several vignettes ago, my favorite picture is really just a counting argument, which is that systems tend to move in the direction of the states that can happen in the most number of microscopic ways. And what I wanted to do now, since we've already introduced and used statistical mechanics several times, is to try to present the idea that this is a different way of stating the same basic ideas. In other words, statistical mechanics, and to be more precise, what I referred to as the Boltzmann Law, which is the relative probabilities of two states that have energies E1 and E2 are given by this ratio of their Boltzmann factors, where once again I remind you that beta is 1 over kBt. So that's, for me, the Boltzmann Law. And you might be saying to yourself, well, how does that square with the second law of thermodynamics? In other words, how would it be that a system could, in a way, borrow energy from the surrounding reservoir? I think it's very important to understand that what this refers to is a situation like me putting an Eppendorf tube in the Pacific Ocean. So what happens is that the contents of that Eppendorf tube will equilibrate with the surrounding ocean without perturbing the ocean itself. The temperature of the ocean is not going to change because we put an Eppendorf tube in it. But the temperature of the Eppendorf tube is definitely going to change because we put it in the ocean. And the reason for that is that there's an exchange of energy. In other words, there's energy being shared between the reservoir, which is the ocean, and the Eppendorf tube. And in this case, if the Eppendorf tube is warmer than the ocean, what will happen is that the kinetic energy of the molecules in the Eppendorf tube, which is there's higher energy there, it's going to diffuse. The momentum is going to diffuse, is another way for you to think of it, so that the energy is more uniformly shared. Just like when I refer to this room, I want to share the space more evenly. If I put all the molecules on one side, I'm not sharing the space in the most sort of fair way. And so a lot of what happens when we look at the world changing and going to some terminal state is that it's moving towards fairness, if you like, sort of democratic distribution of objects in space and in energy and so on. So that's what's going on here. I wanted to just kind of foreshadow this whole thing by showing you this figure that tries to indicate what it is that we're about when we use the Boltzmann distribution. So I could be thinking of a completely isolated system, which is the one that I referred to earlier when I had the partition, and then I let the wheels allow the partition to move, and that was the way we equilibrated pressure and so on. But I could have a system in which the thing I'm interested in is this part, the cube in the middle, but it's also in contact with the reservoir, so this stuff is meant to represent the Pacific Ocean. And now what I have to do when I talk about maximizing the entropy, I have to maximize the entropy of system plus reservoir. I have to do both of those at once. And what I'm telling you without deriving it is that the Boltzmann distribution is basically a way of computing the probabilities of different ways of partitioning the energy. If I put more of the energy in the system, that means I've taken some away from the reservoir, and that becomes less and less likely the more energy I take from the reservoir and give it to the system. That's really what Boltzmann is telling us. So just as a reminder, as a recap, we had this notion of the statistical mechanics protocol. I used it in the context of an ion channel, which you see right here, and that's fine, and that was really good. And what we said is, well, we have to identify the relevant states. That's really enumerating the microstates of the system. And I have a couple of other examples for you to think about. So, if I lay down DNA on a surface, here you see a bunch of AFM images, atomic force microscopy images of DNA on a mica surface, if I remember correctly. And each one of these configurations is a different microstate of the system. And they have different energies. And the reason they have different energies is something that will come up later in the course when we talk about the elastic energy of bending a material. So this guy has more bends sort of than this guy. This one is a little bit more gently bent. This guy has a really tight bend right up here. And so what we're going to find later is that the energy is going to be kappa over 2, and then I'm going to have an energy that looks like this. So this is basically the curvature squared of the elastic rod. And so what we're saying is that this is Hooke's law, basically. It's saying that there's a quadratic penalty for curving the object. And so we can plug this thing, this energy, into Boltzmann to tell us how likely different states will be because they have different energies. So different energy has a different probability. So at any rate, yeah, we have we figure out the states of the system. So here's the states for the DNA. We already talked about the microstates for a receptor ligand system, and here's an example of 4 different microstates of the ligand receptor system. There's just different ways of distributing the ligands in solution, and if you don't like the lattice model, you could have a continuous integral over space. It's the same idea, which is basically how much volume is available for those objects to move around in. So we work out the states. Then what we do is we compute the energies, and then from the energies we compute the Boltzmann weights over here. So basically, the higher the energy, the less likely the state, and that goes back to what I was saying about the fact that really what we're doing is we're maximizing the energy of entropy of system plus reservoir, and what we find is that the probability of the states, the number, so another way of saying it is the number of ways that I could have my system have lots of energy and have the reservoir have less goes down. The more energy I put in the system, the fewer ways I can realize that. And I always liked sort of an analogy with piles of money. If I had a pile of $20 bills and there were 30 people in the room, and I decided to keep all of the money, then there's no ways to distribute. If I let you guys have one of the bills, then the number of ways of distributing that is equal to the number of people. And if I let you guys have 2 of the bills, then there's another number, which is larger. There's more ways that I can distribute 2 bills amongst all of you. And so what's happening is the less and less money I keep, the more ways there are of distributing the money among the reservoir, which is all of you. That's basically what Boltzmann is about. And it's still fundamentally an argument about counting. The probabilities of the states are reckoned by figuring out how many ways can a given state occur, divided by the total number of ways of realizing the system. That's the probability. That's Boltzmann. So this is just a different angle on this notion of maximizing the entropy and the opposite of defiance. It's the compliance. The system complies with the edict of the second law of thermodynamics by going to the state that can happen in the most ways. If I have system plus reservoir, it's a little more subtle because there's fluctuations. So the system is jiggling around. We know that the most likely state is most of the energy in the reservoir, but we can have a little fluctuation where the system gets a little bit more of the energy and it's exponentially less likely, but it's still allowable. And that comes from counting. We count up the number of ways of realizing the different states. I think that was the main message of what I wanted to say with this one. And I think in some sense, this basically prepares us for now starting to think about departures from equilibrium. First, we'll think about that from the phenomenological point of view. And then with that in hand, we'll actually turn to the real world defiance, which is the central preoccupation of this part of the course.